In this video, we'll look at the various mode solvers available in FIMMWAVE. And we'll do so by looking at this preloaded project file we have here. So let's click on the first node in the list called RWG. And you can see here it's a high refractive index, ridge waveguide structure. The mode solver that's most suitable for this type of structure is the FMM solver. So in the solver settings for this waveguide, the FMM solver has been selected, and we'll just calculate two modes just to demonstrate the use of the solver, and we click OK. So click the mode solver, build list, start, and it picks up the two fundamental modes of this structure. The two fundamental modes being EX and EY polarized. The 100 you see here represents 100% EX polarized. 0 means 0% EX polarized and therefore EY polarized. And the number you see in the brackets here is the effective index of the mode. So the reason the FMM solver is suitable for this structure is because it doesn't require a numerical mesh such as the FD solver and the FEM solver requires. The FMM solver works on slices and layers. So if this ridge or even the slices next to the ridge are incredibly wide, this is a very efficient solver to use. However, if we look at the next waveguide in the list, this is the diffused waveguide. This is obviously a structure that isn't built using a series of slices and layers and perhaps isn't as suited to the FMM solver. What we have here is a region in this grid area here of diffused refractive index profile. And if I plot the refractive index, you can see here there's this diffused refractive index profile in this top center here and just diffusing away from that center point. So in this case, this refractive index profile is not neatly divided into slices and layers. So we look at the solver options here. And you can see here we've selected the FDM solver, finite difference mode solver, because it uses a numerical mesh, which seems appropriate for this type of waveguide structure. The mesh parameters here are set here as mode profile resolution. The NX and Y are the number of mesh points. And then in the edit solver palms section, we can also select if we wanted a non-uniform mesh shift as well. Okay, so open the mode solver, build list, start. And you see here the FDM solver is very fast in this case. And we see the fundamentals. And then these are radiation or cladding modes. But the FDM solver is more suitable for this structure here. Now if we take the next mode solver in the list, the photonic crystal fiber. Again, obviously the FMM solver is not suitable. The FDM solver would be okay, but perhaps the most suitable mode solver for this structure is the FEM solver, finite element mode solver. And the reason for that is because it uses a triangular mesh. So the triangular mesh can match the circular profiles quite nicely. So if I click OK, open the mode solver. But before we calculate the modes, let's look at the engine info and actually look at the mesh that we're looking at. So two things to notice. One is a triangular mesh that matches the profile quite nicely with a variable size in the triangles. And also notice that we're only simulating a quarter of the waveguide. We're invoking symmetry, and we've told the solver there's two symmetry planes, and just to make the calculation easier. So build list, start. So here are the fundamental modes in the center here. Again, two different polarizations. And then because we asked the software to calculate 4 in this case, we've got 2 extra modes calculated for the area between the air holes and the boundary. And then finally for this video, let's look at a fiber mode. So I've got a structure here which is based on SMF28 at 1.31 micron wavelength. And obviously, the 3 mode solvers we've seen so far are not the most suitable for a truly cylindrical structure. So we can invoke a different mode solver called a finite difference fiber solver. It's using a finite difference method, but it's the fiber solver version, meaning the numerical resolution, which we see here as a parameter called nres, is just along the radial profile, and then the mode is solved in cylindrical coordinates. So it's set to calculate one mode. There's the mode right there. If I was interested in higher order modes, or if this was a multi-mode fiber, in fact, let's make it a multi-mode fiber. Let's just gonna quadruple the size of the core. And I'm going to calculate 10 modes of a various range of M orders. And then we can see the various high order modes in the core. So the key thing to take away from this video is that FIMMWAVE comes with a whole selection of different mode solver engines that you can choose to use depending on which is most suitable or most efficient or most accurate for the structure that you're calculating.